Hello and welcome everyone to the live class session of week 3. I am Srijan Sen and today I will be taking a live class session on the course Experimental Biochemistry, which is being taught by Dr. Shomode and Dr. Shagata Dasgupta of IIT Kharagpur. So today we would be discussing about spectroscopy and the different aspects of it, and also I would be discussing a few questions which will help you in solving your assignments and other problems. Okay, so let us begin. Okay, today we will be discussing about spectroscopy. So mainly we will be focusing on UV spectroscopy and the fluorescence spectroscopy. So before we move into the different spectroscopies, we have to understand what spectroscopy is and what are the different aspects of it. So there would be different concepts of spectroscopy which would be discussed with you people, and I would be solving a few questions which will help you in solving your assignments as well as giving your exams on this topic. Okay. So what is spectroscopy? So spectroscopy is the interaction of radiation with a sample. It is the study of molecular or the atomic structure of a substance by observation of its interaction with the electromagnetic radiation. So, in spectroscopy, we are studying the molecular or the atomic structure of a particular substance, and how we are studying the molecular and the atomic structure of that particular substance. It is by observing its interaction with the electromagnetic radiation. So if we say spectroscopy from a quantitative point of view, then spectroscopy is used for determining the amount of material in the sample. So we would be determining how much material or what is the amount of material present in the sample. So that is spectroscopy from a quantitative point of view. Now if we speak of spectroscopy from a qualitative point of view, then it is used for identifying the chemical structure of a sample. So from the qualitative point of view, we can tell or we can get informations about the chemical structure of the sample that we want to study or that of which we are observing. So most of us are also aware that many different ways of transmitting energy and these phenomena come together in one physical entity which is called the electromagnetic spectrum. Now this electromagnetic spectrum is the spectrum which we need to keep in mind when we are studying the spectroscopy, and lots of many of us are aware of this the different ways in which the different rays transmit their energy and this phenomena comes into play. Okay. The difference between these sources of radiation is the amount of energy that they radiate, and the radiation from these and other sources covers a range of energies. So all these things combine to give us the electromagnetic spectrum. Now speaking of the electromagnetic spectrum, first we have these set of, you can call the energies or the rays. Okay, so first beginning with, so these rays can be these waves can be classified on the basis of your wavelength, then energy, then frequency. From here we can tell that low energy radiations have longer wavelength and high energy radiations have shorter wavelength. So starting from the left hand side, we have the radio waves, which has the longer wavelength and less energy and less frequency. So we relate this by the equation E equals to hc by lambda or E equals to h nu. Okay, so we have the equation as, well, lambda is the wavelength and c is the speed of light. Also, we can relate this by E equals to h nu is a frequency. So from here we can tell that is inversely proportional with our wavelength and directly proportional with our frequency. That's why with a longer wavelength comes a lesser frequency, and with a lower energy comes your lower frequency. Okay, so on the left hand side we have the radio waves, followed by which we have the microwaves. Then we have your infrared radiation comes, are then after which comes the visible, um, and then we have the ultraviolet radiation, after which we have the x-rays, and with shorter wavelength and higher energy and highest energy and the highest frequency we have the gamma rays. So here you can encounter some questions like which wave has the, or which radiation has the highest wavelength or the lowest energy, and then which radiation or which wave has the shortest wavelength and the highest energy, etc., etc. So these can be, there can be a few questions on this. Also there can be a few questions on this equation where you are given the Planck's constant, then the speed of light and the wavelength, and you're asked to calculate the energy, or you're aware of the frequency, and then you're asked to calculate the energy. So there can be a few MCQs on this. Okay. Now, what is radiation energy and what is its strength? The strength of the radiation energy. So, in radiation energy is the energy which is being radiated. Okay, so the strength of this radiation energy will interact with the molecules in different ways. So, for example, the high energy sources are used for breaking of bonds. Like, so these energy sources are your gamma rays, then your X rays. Also, we have medium energy sources which are used for exciting your electrons. For example, we have the UV visible spectroscopy. Okay, then we have the low energy sources which produce vibrations in the, which produce your vibrations in the chemical bonds. Those are the infrared energy. And the microwaves and your radio waves are very low energy sources which produce rotation in the chemical bonds. So there can be, so from this slide you can get questions on X-rays and gamma rays are used for. Then you're given four options like exciting electrons, then breaking bonds, vibrations in chemical bonds, rotation of the bonds. Okay, so you have to then tick the right answer. Okay, so X-rays and gamma rays you have are for producing breaking of the bonds. Then UV visible we use for exciting of electrons. Then we have the infrared, which are the low energy sources and are used for vibrations. And then we have the very low energy sources, among which we have the microwaves and the radio waves, which are used for the rotation in the chemical bonds. Now, what is this visible spectroscopy? So, before we move on to visible spectroscopy, we have to understand what is color. We all know what color is. So, color is a sensation which occurs when light enters the eye. When light enters the eye and focuses on the retina at the back of the eye. So, this is the retina at the back of our eye. So, where your light focuses, and this light initiates a photochemical reaction in the nerve cells in which is attached to the retina, and then they transmit impulses to the brain from which we can understand the color. we get the sense of a color. So firstly, your eyes detect the light enters through. So firstly, the light enters through your eye, then it gets to your retina. Okay, after which it is detected by the nerve cells which are attached to it, and then they transmit impulses to the brain, from which we can get the stimulation out of our sense of color. So the cells which are present in our eyes includes the cones and the rods. So the cones gives color, and three primary colors, of which we have the red, blue, and green. The rods gives are actually play an important role for the night vision, and they give us the gray or the black color. So all the colors that we actually sense are made up of the three colors along with the white, gray, and black. So the primary colors along with the gray, black color are combined to give us the colors which we see in our daily. Now there are different wavelength range and the color absorbed and the color which is being seen by our eye. So we need to keep in mind that the light which is being absorbed is not the light which is being seen by our eye. So if a particular object is absorbing a light, it does not, but what is the color that we are actually observing? It is not the color that is being absorbed by that particular object, but it is the color that is radiated by that object, or is liberated by that object, is actually what we are observing, or it is the color which our eye can actually detect. So these are the different range of wavelengths which are being absorbed, and in the different ranges, what is the color being absorbed, that is also being given over here. So in the range of 380 to 430. So in the first line it says, when the sample only absorbs light of a single wavelength, the eye sees the complementary colors. So what we are observing are the complementary colors. So in the wavelength of range for 380 to 430. So in the wavelength of range 380 to 430 nanometers, the color absorbed is the violet color. Okay, and the color which is being seen by your eye is the yellowish green. Whereas the color, if yellow green color is being absorbed at 560 to 580, we are observing is violet. So the complementary color. Then at 430 to 480, we are seeing as blue. But when we are observing blue, the color being absorbed is yellow. But when the color absorbed is blue, then we are seeing as yellow. Okay, so then in the range of 480 to 490, we have the color being absorbed is the greenish blue. and we are seeing it as orange. Then at 490 to 500, the color absorbed is blue green and the color seen by our eye is red. Whereas at 500 to 560, the color absorbed is green and the color seen by our eye is purple. At 560 to 580, the color absorbed is yellowish green, but the color seen by our eye is violet. At 580 to 590, the color absorbed is yellow and then the color seen by our eye is blue. At 590 to 610, the color absorbed is orange and the color seen by eye is greenish blue, and the color absorbed when the color absorbed is red, the wavelength range falls at 610 to 750 and the color seen by our eye is bluish green. Okay. So now speaking of the different energy levels on the nature of the energy received. So A0 is the ground state, and it has and each state has different other levels, including like your rotational levels, then it has the vibrational levels, etc. etc. So A0 is our ground state, and we have say a number of electrons in the ground state. So when we are providing UV visible absorption, then the electrons moves from the S0 to the S1 level. Whereas on providing IR spectroscopy, we can only reach up to the vibrational levels of that particular state. And when we are providing microwaves, okay, then we can only reach up to the rotational levels. So depending on which of the levels we want to reach and for which particular state, we can uh, comment on what sort of type of radiation we want to provide. Like for example, we want to move from the S0 to the S1 state, then from the rotational level of S0 to the rotational level of S1 state. That is absorption. Then you have to provide UV visible radiation. Now, if you have to move from a rotational level to the vibrational level. So also in between these levels, there are different sections of these levels or the different levels within inside these levels. So like n equals to 1, then we have n equals to 2, then we have n equals to, so like this it goes on depending on which levels they are on. Okay, so now if we have to reach from a rotational to a vibrational level, then we can provide IR spectroscopy, IR infrared, and then if we go on with the microwaves, then we can move from the ground state level of S0 to the rotational levels. So we can move very little. So the electrons can be excited up to only the rotational levels, or the electrons can be excited to just to the vibrational levels. Or for when we provide UV, the electrons are absorbed to the rotational levels. It undergoes absorption. Now, what is UV visible spectroscopy? So UV radiation has a wavelength range of 220 to 380 nanometer. So we need to keep in mind this range of wavelengths because this would be important and there might be a few short questions on this. And the visible radiation wavelength lies between 380 to 780 nanometer. So the substances can absorb varying amounts of UV or the visible radiation at any particular wavelength. So the colored compounds absorb energy in both the UV and the visible region of the electromagnetic spectrum. Now, substances can be liquids or solids, and the measurements are made with specific instruments, which we call as the spectrophotometers or the spectrometers. Okay, now, modern instruments can be coupled to the microscopes, which allow the solid samples and very small samples of the solids and liquids to be analyzed both quantitatively and qualitatively using this instrument. So, there are instances where these spectrophotometers are attached or coupled with these microscopes uh, to observe as well as analyze them these solid samples and sometimes liquid, sometimes phase separation, etc. So these can be beneficial. Now When we provide a radiation to a sample or a light, let us say we are giving a light to a sample, and that sample has the ability to absorb a part of that light or a part of that radiation and transmit the rest of it. So what is the absorption of that sample? We can understand when we know that the intensity of, when we have a prior information about the intensity of the light which we provided, and the light and the intensity of light which is transmitted. So for example, a wavelength of a light of wavelength 254 nanometer, which is called the incident light, is given to the particular sample, and we know that the intensity of that is I naught. Whereas the transmitted light at wavelength 254 nanometer, we have an intensity of IT. So IT is either equal to I naught or sometimes less than I naught. From there, we can get information about the transmittance as well as absorbance. So how they are related? They are related by a particular equation. I will be coming to it in my future slides. Now, if a particular wavelength of UV or visible radiation can be isolated from the source and passed through the sample through which it absorbs some of the radiation, then the transmitted light intensity is IT. So the previous one was I0, will be less than that of the incident light I0. So if it is absorbing the transmitted IT, that is IT would be less than I0. When a particular sample is which can has the ability to absorb. Now the amount of light which is transmitted with respect to the incident light is known as transmittance, and it is represented by T. So T can be defined as T equals to IT by I naught. So this equation is important because there can be questions related to where you're given the intensity of the transmitted light, and you know that the intensity of the light which of the incident light, and then from there you can calculate transmitter. So in most of the cases we consider the transmitter the intensity of the incident light is 1 or 100, depending on in which you are calculating. So when we are calculating in terms of percentage, then we can so the intensity can be considered as 1, and then there can be say the trans IT is zero point 0.2. Okay, so zero point 0.2 by 1 into 100, so 20% of the light has been transmitted. So there from here we can comment on the transmittance value. So samples can absorb all or none of the transmitted light, and therefore transmittance can be quoted as a percentage. Now coming to absorbance. So absorbance and transmittance are interrelated by this equation. A equals to minus log to the base 10 of transmittance. So when we put the previous formula of put this formula, then we get from here absorbance equals to minus log to the base 10 of IT by I0. And so A equals to minus log to the base 10 of IT by I0, and from here we can, if we remove the negative sign, we get absorbance equals to log to the base 10 of I0 by IT. So this equation is actually an important equation because this will act is important for calculations as well as in calculating your absorbance, and there would be definitely a few numericals related to this equation as well as the equation of transmittance. So like transmittance equals to IT by I0, whereas absorbance equals to log to the base 10 of I0 by IT. Now, if like we know that if we tell in terms of percentage that I0 equals to 100%, then if we know, then there will be also another equation which you can tell that A. So there can be another equation which I am writing on this corner, like, we have log 10, and then we have 100 divided by, because here we know that your intensity of light in percentage is 100%, because when you are providing an incident light, it is 100% of the intensity, and then the reduced intensity would be your IT. So from that we can tell that 100% is the intensity of the, but this is calculated in percentage, say. Okay. And then from here we can get to a equation like this equals to 2 minus. So from this we can also get to this equation. So this is also an important equation which you can keep in mind. So this will also actually simplify your solving of your absorbance formula when you know that. So this value of IT you would be getting in percentage. So the value of this IT you would be getting in percentage. Now, by plotting absorbance versus wavelength, and absorbance spectrum can be generated like this, and the absorption spectra for any random compounds A and B are shown. Now, with the advantage that absorbance measurements are usually linear with concentration, absorption spectra are now used. So, we are aware of a equation that where we know that absorbance equals to epsilon Cl, and here we have a, so we know that absorbance equals to, and L, where L is the path length, C is the concentration, and epsilon is the molar extinction coefficient, and A is the absorbance. So absorbance has a linear relationship with your concentration, and from there the absorption spectra can be generated, but from the absorption wavelength also an absorbance spectrum can also be generated. So from here we can tell that A is, here we can tell that A is absorbing at somewhat your 320, and then you are getting another absorbance at say 360, 350 to 360, whereas B is showing an absorption at around 280, like that. So here you can comment on the from the absorbance spectrum. Now coming to the different laws of spectrometry. So there are two very important and basic laws, and the third one is a combination of the two. So the two important laws are the Lambert's law, where it speaks that absorbance is proportional to the path length of the absorbing medium. So it says that A is proportional to your L, that is the path length. And your Beer's law says that absorbance is proportional to the concentration of the sample. So Beer's law says that absorbance is proportional to your concentration. So from this we get this um, proportionality equation, where absorbance is proportional to your concentration and your path length, and from there we can tell that absorbance equals to epsilon Cl, where your epsilon is the molar extinction coefficient. Now when we move on to calculate the unit of this molar extinction coefficient, we are aware that the concentration is in moles per liter and the path length can be in centimeter. Okay, so usually the path length is given as a default of 1 centimeter, but there can be other numbers also. So depending on the numbers, you can actually calculate this equation. So there will also be a few questions on this equation. A equals to epsilon Cl. You need to keep this equation in mind. This is an important equation. So absorbance does not have any unit, and because it's a ratio and has no units, and we know that from here we can tell that epsilon equals to moles inverse liter centimeter inverse, and we know 1 liter equals to 1000 centimeter cube and 1000 mole. So which is so the if epsilon value is 1000 mole inverse centimeter cube and centimeter inverse. So from here we also get another unit of E, which is 1000 centimeter square mole inverse, and the another one is mole inverse liter centimeter inverse. So there can be an MSQ question like the units or the unit of molar extinction coefficient is slash R. Then you get a few options, among which these two options are there. So mole inverse liter centimeter inverse will also be correct, and then 1000 centimeter square mole inverse will also be the correct answer. Now, what is the importance of this Lambert-Beer's law? So, the importance is that we can calculate the concentration as well as the molar from this absorbance concentration, and if your path length is known, then the molar extinction coefficient of a sample can be calculated. Okay, so the molar extinction coefficient of a particular substance is supposed to be known by us or has to be calculated experimentally. So now if when we go on move on to calculate things experimentally, how we do it. So first here we have considered that E and L are, that is epsilon and L are constant, whereas we are actually wanting to find out this epsilon value. Okay, and we know this equation, absorbance equals to epsilon Cl, and absorbance is proportional to your concentration and has a linear relationship. So this is what is known to us. So how we do it? We prepare standards of the analyte to be quantified at known and different concentrations and measure the absorbance at a specified wavelength. Now you keep the wavelength specific, and then you want to prepare the standards of these analyte at different concentration, and then you measure the absorbance using you can use a cuvette. Then we prepare this calibration curve of absorbance versus concentration, and then from measuring the concentration of the absorbance of the sample and the concentration of the analyte in the sample is can be obtained from the calibration curve, and now from the slope, and on calculating the slope we can actually get your epsilon value. So the slope is and then L, but when your L is 1 centimeter, then we can actually neglect this L. So actually when you also know the path length, so the path length is also known to us, so we can only tell that the slope is epsilon. So from these graph or from these calibration curve, we can calculate the epsilon of a analyte whose molar extinction coefficient is not known to us, or a random sample is given to us and are asked to find out the molar extinction coefficient of that particular sample, then we can use this method in calculating this by drawing the calibration curve. Now coming to the Jablonski diagram. So before moving on to the Jablonski diagram, we would be taking a minute or two of a break before we move on to the Jablonski diagram. So what is this Jablonski diagram? So firstly, we need to know before we go on to the Jablonski diagram or before we are understanding this Jablonski diagram, we need to understand three new terms. One is absorption, one is fluorescence, and one is phosphorescence. And how these three are interrelated. So we know that when the electrons are mostly populated in the ground state level unless they are excited to higher levels. So when the electrons are excited from the ground state level, they move to the higher levels. That is, you can say your, now we have the ground state level as your S0, then we have other levels like S1, S2, we have T1, T2. So S are the singlet state and T is the triplet state. Okay, now we are exciting electrons from the ground state level to the higher levels, say your S1 and the S2. And it has been already shown in the previous slides that each level has other sub levels of like your vibrational levels, then your rotational levels, etc. So on absorption from the electrons can move to the vibrational level as well as your rotational levels to any of the levels. Now we are absorbing or we are exciting the electron from an S0 to an S1 level or an S2 level, let us assume. And then by this internal conversion, the electron is actually losing its energy and moving to a lower level. Now when we are exciting to an S2 level, after losing its energy, it moves down to the S1 level. Now when this loss of energy is bringing the electron is bringing the electron from a higher level to a lower level of the same state. What do we mean by the same state is that you can tell from a singlet state to a singlet state, or from a triplet state to a triplet state. Then we call this phenomenon as the internal conversion, because it is occurring between two same states. That's why we call it as an internal conversion. So after absorption to a higher level, when it loses its energy and moves down to a lower level via your internal conversion, and from that is now the electron is present from the S2 to an S1 level, and after the energy which is being radiated is termed as your fluorescence. Okay, so first the electron is absorbed to a higher levels, say Sn level, and then it loses its energy and moves to an Sn minus 1th level via your internal conversion. And then from that Sn and then from your Sn minus 1th level it moves to the ground state level. So via radiation of an energy, so this we term as your fluorescence. Whereas from the now the electron say is present in the n minus is n minus 1th level, but via your intersystem crossing the electron moves to the triplet state of that same level, that is a Tn minus 1 level. Okay, so now when the electron moves from an Sn minus 1 to your Tn minus 1th level, because the absorption has occurred in the Snth level, so or there can be not only Sn minus 1 or Tn minus 1, from Sn minus 2 to Ttn minus 2, or S you can tell n minus m to Tn minus m. So this can happen, and then by your intersystem crossing, when the electron loses its energy and moves to a different state, that is when we move from a singlet to a triplet state via your intersystem crossing, then uh, after which when the energy is radiated, we call that as phosphorescence. So now what is now summarizing the thing, so fluorescence is what we call as absorption plus loss of energy, but the electron stays in the same state but at a lower energy, and then the energy radiated is fluorescence. Whereas so here internal conversion occurs, whereas first the electron is excited to a higher state, say a higher singlet state, and then via the loss of energy it moves to the S1 state, and then it moves to the triplet state via your intersystem crossing, and then the energy radiated is termed as phosphorescence. So here we can see that S0 to S2 is absorption, or an S0 to S1, and then from S1 to S0 is your fluorescence, and then from T1 to S0, because from S1 it has moved to T1, and then from T1 to S0 is termed as phosphorescence. Okay, so this is the same picture. You can go through it. So this entire concept of absorption followed by your internal conversion and phosphorescence, then absorption, then your intersystem crossing, then phosphorescence, is the entire thing is termed as a Jablonski diagram. Now there are different energy levels of the molecular orbitals. Now if we look into the structure of these you can call this as an aldehyde or a ketone, because this is the formaldehyde, and so for these particular molecule we are looking at the CO molecular orbitals. Okay, so we know that carbon has a electronic configuration of 1s2, 2s2 and 2p2, whereas oxygen is 1s2, 2s2 and 2p4. So oxygen has two lone pairs. So when this so firstly, how we draw these molecular orbitals. So before drawing these molecular orbitals, we have the atomic orbitals which actually combine to form the molecular orbital. So we have the bonding, non-bonding and the anti-bonding orbital. So these two are the bonding orbitals. Then we have the non-bonding orbital and the anti-bonding orbitals. The anti-bonding orbitals are at higher energy compared to your non-bonding and then compared to your bonding. So bonding orbitals are placed at very low energies. And the filling of these orbitals occurs by your following your Pauli's exclusion principle as well as your Hund's rule. The firstly the lower energy molecular orbitals are filled and then only the higher orbitals can be filled up. So in the outer shell of the two atoms of carbon and oxygen, we have 4 and 6 electrons respectively, but here we are not looking at the S cell of carbon and oxygen, so only looking at the P cell. We have for carbon is 2 and for oxygen is 4. Okay, so 2p2 and 2p4 respectively, so combining to get 6 electrons. So these are the 6 electrons which are represented over here, and if we look into the molecular orbital of the CO, we will be seeing that this is the actual orientation of the molecular orbitals. But okay, so LUMO is the lowest unoccupied molecular orbital and HOMO is the highest occupied molecular orbital. So here in this case, so highest occupied molecular orbital is a non-bonding orbital, whereas the lowest unoccupied molecular orbital is the pi star, that is your pi antibonding orbital. But we need to keep one thing in mind, that unless and until our lower energy levels are filled up, we cannot fill up the higher orbitals. So these are the cases of excitation, but these are not the cases where the electrons can be filled randomly. So the random filling of electrons is not possible over here. Okay. So now, firstly, we fill up the electrons, and there are the 6 electrons. Now, there can be transitions. Now, but transitions are the movement of electrons from a particular lower energy level to a higher energy level, or vice versa. Okay. So, in this case, it is a sigma to sigma star transition, and in this case where the electron from the sigma bonding is moves to the sigma antibonding. So the electron moves from here to, okay, and then from the non-bonding orbital it can move to the antibonding orbital of sigma as well. So here we are also observing a electronic transition from N to sigma star. Also, we see other transitions like pi to pi star transition, and then we have your into pi star transition. So if we look at the energy, so now when we arrange these transitions based on the energy, then we can tell that sigma to sigma star has the highest energy. Then we have sigma to your pi star, that is your from here to this transition. Okay, so this is your transition, and then we have in between is the N to pi star transition, and after which we have your pi to pi star transition, and the lowest energy is your N to pi star transition, because these two orbitals are located very close to each other. So now from this you can be asked questions like uh, the highest among the following transitions which has the highest energy or which has the highest frequency. Also, there can be questions like which will have the highest wavelength or which transition will absorb at a higher wavelength or at a lower wavelength. Then, from the previously said equation, like E equals to hc by lambda, you can tell that as the energy increases, your lambda value decreases, and as your energy value increases, your wavelength also increase, your frequency also increases. So from this we can actually comment on the energy as well as the wavelength and your frequency at different transition at for the particular or the different transitions. Now coming to the Stokes shift. Now, Stokes shift is the gap between the maximum of the first absorption band and the maximum of the fluorescence spectrum. So, the difference between this one and your this one is known as the Stokes shift. So, loss of vibrational energy in the excited state as a collision, as heat by collision with the solvent. So, vibrational energy from the excited state is lost in the form of heat by collision with the sample. So now the electrons are absorbed to the different vibrational levels of S1, and a few of the energy is lost in the form of heat and will reach the V0 or the vibrational level 0 of the S1 state, after which we can observe fluorescence. Now, some examples of the different fluorophores are your fluorescein, which has this particular structure, and another one is the ethidium bromide, which is bound to DNA. So, ethidium bromide is a chelating agent which binds to the DNA and actually it fluoresces under your UV. So this is the structure. So there can be only a few questions like name a few fluorophores or pick the correct fluorophores, and there can be some MSQs. You do not have to actually keep the structure in your mind. This is just for your support informations. Which okay, so fluorescein has an absorbance at say 490 nanometer, and it fluoresces at around your 520 525 nanometer, whereas the lithium bromide has an absorbance at say 520 nanometer, and it shows fluorescence at 620 nanometer. Okay, so these are a few examples of the fluorophores. Now coming to the concept of lifetime. Now the excited state decays exponentially with time. So this is the equation, and in this manner how we relate it. So here I represents the intensity at time t, like your transmission, like for the formula of transmittance. If you can recollect the formula of transmittance. Uh, in the formula of transmittance, we had that T equals to IT by I0. In the similar manner, so I is the intensity at some time T, I0 is the initial intensity at time 0, and then we have tau, which is the lifeline of the excited state, and from here we can calculate the rate constant of fluorescence, that is your kf, which is equals to 1 by tau. So there can be questions like you are given the intensity at time t, and then you know your prior intensity, or this you can calculate as in the form of percentage as well, where you consider I0 as 1, and then you know I value, and from there you can calculate your tau value if you know the time t, and then From there, you can calculate the rate constant of your fluorescence. So the Kf value can be calculated. Now, what is quantum yield? So quantum yield is the ratio of your photons emitted to the photons absorbed by the system. Now it is the number of fluorescence quanta emitted divided by the number of quanta adsorbed to a singlet excited state. Ratio of photons emitted to the photons absorbed. So quantum yield, if we speak simply, is your amount of quanta. So quanta is packets, we call this as packets of energy. So the number of packets of energy which you have emitted divided by the number of packets which you have absorbed in an excited state. So simply speaking, this is the ratio of the photons which is being emitted and the to the ratio of photons being absorbed. So this is a ratio of two quantities. So there can be also a few questions on this quantum yield problem, and then you are given that this much amount of energy, photons are being absorbed and has been absorbed, and this was the amount of photons emitted. So calculate the quantum yield. So from this you can comment on the quantum yield. So this is a this is a complex equation, but this K value, which is our fluorescence, so the K value is our rate constant for fluorescence. So this value is dependent on other factors as well, and it is a summation of your fluorescence radiative rate. Then you have your internal conversion, which involves the collision with the solvent plus your internal vibrational mode, and this value increases with your temperature. Then we have the quenching factor, which occurs when collision with the solute molecules such as your oxygen takes place. Then we also have factors like your energy transfer. Then you have factors which are included from the reaction from excited state, and then we have K value from your inter-system crossing, which is a forbidden, but it has to be considered. So when a electron is excited from an S0 to an S1 state via the energy provided is your H nu A, and then here it is your fluorescence radiative rate is your H nu F. Then you have your internal conversion, then you have your quenching factors, then we have your inter system crossing, followed by your reaction from the reaction from your excited states. Okay, so from this we get a big equation of K equals to the summation of your all these vectors, and from this we can get the ultimately the K value. So now coming to polarization. So a molecule of our interest or a molecule can be randomly oriented in a rigid matrix, and plane polarized light is used as the excitation source. So the degree of polarization is defined as your P, where P is equal to your intensities at of the observed quantity in the parallel component and the perpendicular component divided by the addition of the two things. Firstly, we have the intensity of the observed at parallel component minus your perpendicular component divided by your observing your intensity at your observed at perpendicular component plus your parallel component. So this is defined as the degree of polarization. Also now if we know that the value of alpha, now alpha is the angle between the mission and the absorption transition moments. So now if the alpha value is known, it is so polarization can be also be expressed as 3 cos square alpha minus 1 divided by cos square alpha plus 3. So from this also we can calculate our degree of polarization or the p value. Now, if your alpha is 0 degrees, then P equals to plus half, whereas if alpha is 90 degrees, then P equals to minus 1 by. Now, coming to the inner filter effect. So, if we see that at low concentration, the emission of light is uniform from the front to the back of the sample. But as the concentration is increased, more light is emitted from the front than the back, because at higher concentration the light may not be able to reach to the utmost end of the cuvette, and so this can actually create so this concentration factor acts as a filter. But this filter is because of the intrinsic property of your sample. So the concentration, on increasing the concentration, it actually acts as a filter. So this is called the inner filter effect. So since the emitted light from the middle of the cuvette is detected, the concentration must be low to assure accurate measurements. So at low concentration, it is not much of a problem, because then your concentration is okay enough to for the light to penetrate and get accurate results. But at high concentration, the more of the light is emitted in the front but not at the back. So to assure accurate results and your 5F calculations, we need to keep the concentration as much low as possible. Now, speaking on the intrinsic fluorescence of the proteins and peptides, so if we see that tryptophan, so if we see tryptophan, it has a lifetime of 2.6 nanoseconds, and it has an absorption wavelength of 20 nanometer and an absorptivity of 5600. Whereas it has a fluorescence, and it fluoresces at a wavelength of 348 nanometer, and it has a quantum yield of zero point 0.2. Whereas for tyrosine, it has a lifetime of 3.6 nanoseconds. It has a wavelength of 274 nanometer and an absorptivity of 14 nanometer. It fluoresces at 303 nanometer and has a quantum yield of 0.14. So these amino acids are actually important for any of the proteins, because these amino acids have your chromophoric moiety, or you can call has aromatic rings to its side chains, which are actually important for the absorption or getting the absorption spectra of a protein. Now, for if a protein has no tryptophan or tyrosine or phenylalanine, then the absorption spectra of the protein cannot be determined, because these are actually the chromophoric moieties which are actually important to be present in the protein to get the absorption peak. Now, this absorption peak is also important when you are actually purifying your protein or calculating your the concentration of the protein. So these are important. So, but if these amino acids lack inside your protein, then the absorption is difficult to be calculated. So higher number of tryptophans and tyrosines and phenylalanines are good for your protein. So therefore, these three amino acids are actually three important amino acids for your protein, because we would be always looking from a protein point of view, because amino acids are the building blocks. And what is a brick without a house? So a brick is like a brick only, but we have to look at as to what would be the situation when these bricks combine to form a house. So that's why we are looking from a protein point of view. Now, if we see, phenylalanine has a lifetime of 6.4 nanoseconds, and it has an absorption. of at wavelength 257 nanometer and an absorptivity of 200, and it fluoresces at 282 nanometer and has a quantum yield of 0.04. So this is also a table where you can get the substance and the condition and the absorption wavelength, then your epsilon, the molar extinction coefficient value, then you can get the fluorescence wavelength, then your quantum yield followed by a tau f factor, and then your sensitivity can also be got from this table. So you can go through this table. Okay, now before moving on to the practice problems, let us take a 2 minutes of break, after which we would be moving on with the practice problems. And these practice problems are important because this will actually help you in solving your assignments and the future exams which you will be giving. Okay, so let us solve a few practice problems. So the first question says the region in the electromagnetic spectrum which has the maximum wavelength is. So if we move back to the electromagnetic spectrum where we spoke about the electromagnetic spectrum, so we have seen that radio waves have the so the question says which has the maximum wavelength. So if we see the maximum wavelength is for the radio waves, the shortest wavelength is for the gamma rays. So when we move on, when we go to the question, we can tell that the maximum wavelength is for the radio waves region. there can also be questions like which has the minimum wavelength or which has the maximum frequency and energy. So then you can from the equation equals to h nu or hc by lambda, you can comment on that. Okay. Now the next question is energy of radiation varies proportionally with. So the equation of so the equation is equals to, so E equals to hc by lambda, or you can tell E equals to h nu. So at the same time, E cannot be proportional with your lambda or your frequency, but actually the equation is E equals to h nu. So therefore the energy of a radiation varies proportionally with its frequency is the right option. Now the type of radiation generally used for electronic excitation. So for the electronic excitation, okay, so what sort of radiations can be used? So we know have seen that microwaves are used for your molecular rotations. Then your infrared is used for molecular vibrations. Then X-rays and UVs have high frequency and high energy. Therefore, they are used for your electronic excitation. So from here we can tell that option A and C are correct. Now, which of the following wavelength ranges is associated with your UV spectroscopy? Now, okay, so the range of your so the options which are given to us are zero point 0.1 to 10 nanometer, then 200 to 400 nanometer, then we have 380 to 700 nanometer, and 700 to 1000 nanometer. So zero point 0.1 to 10 nanometer is for a X-ray. 200 to 400 nanometer is for your UV spectra. Okay. 380 to 700 nanometer is all known to us. It is in the visible region. And your 700 to 1000 nanometer is for your IR spectroscopy. So these are the few. That's why I was telling that the wavelength ranges should be kept in mind, because there can be a few questions on this. So that's why I've written all of them beside. So now the question can be interchanged from UV spectroscopy to IR, or maybe visible or X-ray. So from this you can actually relate and tell which region falls in the which wavelength range. So the right answer is B. Okay. The next problem says UV spectrometer uses two light sources from the deuterium lamp and your tungsten lamp. Now, if the tungsten lamp stops working, then in which way the measurement will be affected if the scan uh, will be affected if the scan range is set from 200 to 800 nanometer. Now, if we see that the deuterium lamp is actually You can tell that the deuterium lamp is a part of the UV source, okay, is associated with the UV source, and your tungsten filament lamp is associated with the visible light source. Okay, so now if we know that the range of the UV source and the tungsten and the visible light source, then we can actually solve this. We can actually simplify this question. So the deuterium lamp falls in the range of can detect in the range of you can say in the UV source. So it is 160 to 375 nanometer. And your tungsten lamp falls under the category of your visible light source, so it will fall in the range of your 350 to 800 nanometer. Now the question says that if the tungsten lamp, that is if this tungsten lamp stops working, in which way would the measurements be affected if the scan is set from range of 200 to 800? Will be so the light will pass through the sample cell only, but not through the reference cell. Light will pass through both the cells, but up to a specific wavelength. Excess light will pass through the reference cell as compared to the sample cell, and lower wavelength light will not pass through both the sample and the reference cell. So the correct option would be so your tungsten lamp is not working. So your tungsten lamp stops working. So you cannot detect in the range of 350 to 800 nanometer. So the light will pass through both the cells, but up to a specific wavelength. That is, what is the specific wavelength? So the specific wavelength is in this particular range only you can actually detect. Otherwise, you cannot. But it can. But the light will pass through both the cells. Okay, now the next question is tryptophan, tyrosine, and phenylalanine absorbs in the UV region, mainly due to their. So as I was speaking, so they mainly absorb due to their chromophoric moiety, and they have aromatic rings which are actually absorb and gives us the which are actually important for obtaining the absorption peak. That's why these three amino acids are important, and because of these three amino acids, proteins have an absorption at 280 nanometer. So these three amino acids are important for getting an absorption at your 280 nanometer, whereas your DNA has an absorption at 260 nanometer. So because of the chromophoric moiety, these three amino acids absorbs in the UV region. Now the next question is a graduate student is going to measure the concentration of BSA protein in phosphate buffer, for which he has taken two solutions in two cuvettes C1 and C2. The solution he should take during baseline correction. So the solutions which that person should take in during baseline correction. So during baseline correction, we set as a blank. So the blank is the one which we in which your particular sample is in. Okay. So for example, if the sample is in water, then your blank should be water, and if your sample is in a particular buffer, for in this case it is the phosphate buffer, then your particular then the solvent used for your baseline correction should also be that particular buffer of that particular pH. Okay, so here so the options given are C1 BSA, C2 phosphate buffer, which is not okay. C1 equals to say BSA. So BSA is the protein sample in phosphate buffer. So the protein cannot be used as a baseline correction. Then we won't be getting any absorbance, and we would be getting an absorbance of 0, and then C1 phosphate buffer and C2 BSA, which is also not correct. So D C1 equals to C2, which is the phosphate buffer. So the buffer in which a sample is present has to be used for baseline corrections. For accurate measurements of fluorescence emission, the cuvette should be. So the fluorescence cuvettes are made with quartz, since quartz transmits your 80% light, which is higher than glass or plastic, and have all your four sides transparent. So therefore, the correct option is D, that it has to be made of quartz with all your four sides should be transparent. So this is your cuvette should be made up of, it has to be transparent and should be made of quartz. So this is another thing which you should keep in mind about the cuvette. Now the next question says the double beam spectrophotometer differs from a single beam spectrophotometer since the former. So before I tell the answer, let's see the diagram. Okay, so it tells that so the light source moves from the chopper and is reflected by, and there is a reference beam. So a part of the light as the sample beam moves to the sample cell where we have the flame or the furnace, and then comes the monochromator followed by the detector. And another wave after the light source from the chopper moves as the reference beam and is reflected to the monochromator followed by the detector. So the chopper splits the light into two parts, which passes through the reference and the sample cuvette. Okay, so first thing is that the chopper splits it, which is also correct, and both the sample can be measured simultaneously. This is also correct. So A and C both are correct, and this is the diagram of your double beam spectrophotometer, which you can look to check. So another time I'm repeating it. First, there is a light source, and it moves to the chopper where it splits the light into two parts, which passes to the reference and the sample cuvettes. Now the reference beam is reflected to the monochromator and then to the detector, where the sample beam moves to the sample cell where we have the flame and the furnace, after which we encounter the monochromator and then it is being detected. Okay, so both the sample and the reference cuvettes can be measured simultaneously is also correct, and the chopper splits the light into two parts, which passes to the reference and the sample cuvette is also the correct option. Now the next question says an electron is excited from non-bonding orbital to a pi orbital. The correct notation would be. So the non-bonding orbital is Rn, and for our pi anti-bonding, so pi is this, and for anti-bonding we use it as star. So N to pi star is the right option. So we have that in C. Now the UV absorbance at 278 nanometer in RNase protein is solely due to tyrosine residues present in the protein. Now during an experiment, the absorbance of X protein comes to zero point 0.4 at 278 nanometer. When measured using a cell of path length 10 millimeter, then the concentration of the protein present in the cuvette is around. So here the molar extinction coefficient is given. So for using the equation E epsilon Cl equals to A, and your path length is 10 millimeter, which is your 1 centimeter, and the epsilon value is given in the particular unit, so 9800. And from here we can calculate the concentration as absorbance divided by your epsilon and L. So here we get the value of your concentration to be 40 micromolar. So B is the right option. So here all the values are given. So from related to this question, you can also be asked to calculate sometimes the absorbance, sometimes the molar extinction coefficient. So here we have four quantities, of which three would be given and the other one you would be asked to find. So from this is are the common questions you can expect in your assignments and your exams as well. Now coming to the next question, the role of the entrance monochromator in the fluorescence spectrometer. So the entrance monochromators are actually used for selecting your specific wavelength that is what we call as the excitation wavelength. So your entrance monochromator selects your excitation wavelength which will pass through the sample. So the options given here are pass polarized light, select light of a range of wavelength that is same time, select light of specific wavelength and prevent scattering of light from the sample. So it will actually help to select light of a specific wavelength. The maximum absorption intensity for a protein sample is found to be 278 nanometer during UV measurement. The preferable emission wavelength should start at. So the emission should start at least your 10 to 15 nanometer ahead of your excitation wavelength. Since we have seen in the Jablonski diagram that the molecular once excited um, to the S2 state, from an S0 state it comes down to a lowest vibrational level of S1. Now the energy gap from your two states, that is you can say your S1 and the S2 state, is should be we know that the energy gap between the S0 and S1 is lower than that of your S0 and S2. Hence your fluorescence wavelength is in the higher range than your excitation wavelength, because we have seen that your energy is inversely proportional to your lambda. So however much higher the wavelength should be avoided, since you might be missing your emission maximum. So therefore, we can select or we can, the preferable emission wavelength should be somewhat 10 to 15 added to your added to the given value of your maximum absorption intensity. Okay, so 278 plus 10 to 15, if we do, we are getting a value of somewhere around 295 nanometer. So this is the correct option. So this value, so it has been set a minimum. Uh, so at least 10 to 15 it should be. So this value plus your 10 to 15. Okay. So we get the preferable emission wavelength. The next question says, while taking the fluorescence emission of lysozyme protein having phenylalanine, tryptophan and tyrosine, one should select the excitation wavelength for. So one should always, because if we see at the intrinsic properties of the particular amino acids of tryptophan, tyrosine and phenylalanine, we have seen that tryptophan is ahead of the other two from all perspectives. You say from the perspective of quantum yield or your absorptivity as well as your lifetime. So tryptophan is much ahead. So we should always be targeting your tryptophan residue, because tyrosine and phenylalanine are much lower quantum as compared to your tryptophan, and at the same time tryptophan has higher absorptivity and your higher lifetime compared to the other two amino acids. Therefore, tryptophan residue should be targeted, since other residues have lower quantum and other factors. Okay, so other options there are tryptophan residue, since tyrosine is non-fluorescent, which is not correct. Your tyrosine, tyrosine, since tryptophan and phenylalanine is non-fluorescent, that is also not correct. And either tryptophan or tyrosine is non-fluorescent, so this is not correct. So the right option. So C is the right option. The next question is, the concentration of the protein should be kept low during fluorescence experiment in order to. So as I have spoken, in highly concentrated solution, the excited beam is attenuated by the sample, so that only the surface facing the excitation beam fluoresces strongly. But as we calculate the absorbance from the center of the cuvette, which is imaged by the emission monochromator in the fluorescence spectrometer, the lower fluorescence emission which will affect the signal which is being detected. So in order to avoid your inner filter effect at higher concentration, therefore the concentration is set as low. And because at higher concentration your sample acts as a filter to the light. Therefore, we get inaccurate results. So therefore, in order to avoid inner filter effect, the concentration should be kept as low as possible. Okay, so I thank you all. Um, and so I hope this lecture would definitely be helping you in solving your assignments and encountering other problems, solving your problems. So that's all from my part, and that's all from today's lecture of week 3. I hope to meet you in the next week. Okay, so thank you.